So in these videos, we're going to go over the atomic theory. So by this point, you've already spent some time researching the history of the atom, some of the scientists involved, what their experiments they did, and what discoveries came out of it. So we'll just go ahead and jump into the structure of an atom. So for the vocabulary, we'll be talking about atoms, protons, neutron, electron, nucleus, atomic number, atomic mass, isotope, and ion. And by the end of this video, you'll know what each of these are and you'll understand what they are each used for. All right, so let's go ahead and talk about atoms. So we've talked about matter quite a bit up to this point. So we know that everything physical that we can experience, the desk you're sitting at, the computer you're using, the air that you breathe, the food that you eat, those are all examples of matter. And all of matter will be made up of these tiny little atoms. So you should know that atoms are made mostly of empty space, but all of their mass and all of the interesting stuff that's going on with them is found in the nucleus. So the nucleus is the center of the atom, and it's very densely packed together. This is where all the mass is concentrated, and then on these rings that you're seeing, that's really just the empty space. They're just there to show you what space the atom would take up. And so just to put this into a little perspective, because this diagram can be a little misleading, you should keep in mind that if you were to compare the size of the nucleus compared to the whole size of the atom, if you scaled up the nucleus to the size of a grain of sand, then the whole size of the atom, everything that is empty space inside the atom, would be the size of a baseball stadium. So that's a really big difference, and it's just the way that this nature is so crazy is just that everything for the atom is concentrated in this tiny little point, and then there's all this empty space around it. All right, so now if all of matter is made up of atoms, you might ask the question, so what are atoms made of? And so we actually have these three basic particles, and these are called the subatomic particles, right? They're smaller than an atom, they make up the atoms. And so these are the protons, neutrons, and electrons. And actually, in a diagram like this, it's kind of hard to tell what's going on with it. So we're going to switch over to a new type of diagram. And so in this one, really what's changing on here is that for the nucleus, we have two different particles that we look at for our nucleus. So these are the protons. So these orange orbs that we have on here, these will be our protons. And so they have a positive charge of +1. Each proton will have an atomic mass of 1 atomic mass unit. That's the unit that we'll be using to count these, just AMU. And again, these protons are found inside of the nucleus. Now, the other orb, the gray ones that go along with our protons, again, they're very similar to the proton. These are the neutrons, and they're also found in the nucleus, same place as the protons, and they have the same mass too, just 1 atomic mass unit. What's different between these two is that the charge the neutrons have is 0, so these are a neutral particle. So you can think of it that way, that protons are positive and neutrons are neutral. All right, and the last type of particle we have on here is the electrons, and these are the most different from the other two that we just talked about. And so notice that these are not found in the nucleus. They go all the way around the nucleus. They're always flying by, and they don't stay put in any one place, and they essentially have no mass. All right, so they have a little bit of mass, but it's kind of like saying that you have a $100 bill and 3 pennies. The 3 pennies aren't really adding that much money that you have. So basically, you still have just $100. But now, what's different, or what's similar and opposite of the other ones that we've seen, is that the electrons have a negative charge of -1. All right, so it's kind of like the protons have a positive charge of +1. The electrons are exactly the opposite of that, where they have a charge of -1. And so this is important because the atoms that we see, that we study, these are electrically neutral. They don't have an electrical charge, and this is because the number of protons and the number of electrons will balance out, and they cancel out the charges of each other. So in this one, if we just count 1 and 2 protons, each one is worth +1. So overall, we have +2 for our protons, The electrons, we have -1, -2. Again, +2 and -2, they completely cancel each other out, and so this would be a neutrally charged atom. All right, so now, we said that all of matter is made of atoms. But if we take two examples of physical matter that we have, right, we might have this GT Mustang and then this delicious hamburger. And so hopefully you know that these are a little bit different from each other, right? They don't work exactly the same way, they don't do the same things. So now, if these are both made of atoms, these are both physical matter, how can they still act so differently? The reason for this is that we can have different types of atoms, which we call elements. And all these different elements have very unique properties. They're all different from each other. Now we have a list of all these different elements that we see in nature, and we find that in the periodic table of elements. So we're not going to get too into detail into the periodic table of elements. In this unit, that's really more for the next unit. We'll be covering the trends and the history and the organization of all this periodic table. But for now, all you need to know is that this is where we pull information for the different properties of our elements. All right, so we've talked about all of matter being made of atoms and all atoms being made of the same subatomic particles, protons, neutrons, and electrons. So now, how can we have these different elements being made of these same things, but they still have different properties? And so never mind. So just something to go over on this one, just give you some basic information on these element diagrams, is that we have the chemical symbol in the center, where this is just a 1 or 2 letter abbreviation of the name of the element. Right underneath that, we have the chemical name. So in here we have hydrogen, we have helium, and we have beryllium. These would be abbreviated as H, He, and Be. And the last number on here that is really important to what we're about to talk about is the one in the top left corner. So that will be our atomic number. This atomic number is important because it tells us exactly the number of protons in an element, and it's really the number of protons that tells us what an element is. This is the defining characteristic of an element, is just the number of protons. And so when we're reading these diagrams, when we see here hydrogen, that it has an atomic number of 1, we know that if we were to build an atomic model for it, it would just have 1 proton in the nucleus. For helium, with an atomic number of 2, if we were to build that model, it would have 2 protons in the nucleus. And finally, for beryllium, and with an atomic number of 4, you can guess what's coming next. We have a model with 4 protons in the nucleus. Now, let's talk about the atomic mass of an atom. So we've talked about the mass being concentrated in the nucleus of the atom, right? And so if we take these two examples, we know that we have different numbers of protons and different number of neutrons. And it's these particles that give the atom its mass, right? And so we can put this into just a very simple addition formula, where if we count the number of protons in an atom and the number of neutrons, together, this gives us the atomic mass of the atom. And so remember that each one of these, both protons and neutrons, they're worth the same amount. They're always 1 atomic mass unit. All right, so if we were to calculate this one out, if we look on here, we have 2 protons in orange, we have 2 neutrons in gray. And if we add that together, we get the mass of this particle is 4 atomic mass units. Sorry, I should have said the mass of this atom is 4 mass units. And same thing for this example, if we have 1, 2, 3, and 4 protons, and then 1, 2, 3, 4, 5 neutrons, add that together, 4 plus 5, you get 9 atomic mass units. All right, so now, we just talked about how every element is different from each other because of the number of protons that they have, right? So this is that defining characteristic of what makes hydrogen and helium different, is that they have different number of protons. But now, sometimes we can have atoms of the same element, the same number of protons, and they have different masses. So they're slightly different from each other. And so this happens because we can have a different number of neutrons and it doesn't really affect the element that we have. So in this example that we have here, we have 2 protons. And in the second example, we have 2 protons again. And so both of these would be helium because they have that same atomic number as 2. Right, so 2 protons and 2 protons defines our helium atom. But you can see that from the gray particles that we have 2 on here and we have 1, 2, 3, 4 on this. They're not changing the fact that it's helium, but it's only changing how much it weighs. So if we were to count that out, 2 protons plus 2 neutrons, we have 4 atomic mass units. In the right example, we have 2 protons and 4 neutrons, we get 6 atomic mass units. So now we have 2 atoms of helium, same number of protons, but they have different masses, again, from the different number of neutrons. And when we have this, we give those atoms a different name for each. These are just called isotopes. These are atoms of the same element, but they have a different mass and a different number of neutrons. All right, so let's get into the notation, how we tell these isotopes apart for when it's important for us to know. All right, so the one way to write these different isotopes is that we will take oxygen and we'll just give it a number, 16. So in this example, we have the element name and we also have the total mass of it. All right, so now remember that our formula for the atomic mass was that the protons and the neutrons are added together to get that mass. And now if we pull up our information on oxygen, and we have this number in the top left, this is our atomic number, and it tells us the number of protons that we have. So for these 2 oxygen atoms, they have the same number of protons. They have to because they're both oxygen. So we have 8. So now what makes up the rest of the mass to get to this number 16 on this is the number of neutrons. So now if you have 8 and you want to get it to 16, you have to add 8 more. So in this, we would add 8 neutrons to get to our mass of 16. The second example, right, you have a different mass number, but the same number of neutrons. The only thing you can have different on this one is the number of neutrons that you're using. So in this, we'll add 10 neutrons because 10 plus 8 will give us 18. All right, so if we try this again with a different element, let's say we have carbon 12 and carbon 13. Again, we pull up our information on carbon, atomic number of 6, so you know that both of these will have 6 protons. You can't change that about them. But then to get to that final mass for each of these isotopes, we just need to add the rest to get to 12 in this case. So add 6 more neutrons in carbon 12 to get carbon 12 and carbon 13, you need 7 more neutrons to get to the mass. And so one last thing to talk about for when we're talking about the mass of an atom is this bottom number right here that we haven't talked about in our element diagrams. And so it's called the average atomic mass, and it might be a little confusing because as we talked about before with the isotopes, we know that this carbon 12 will have a mass of 12 atomic mass units because it's made of 6 protons and 6 neutrons, right? So it's very close to this number on here, but it's not exact, is it? We have 12.011. So from what we talked about, we don't really know where this 0.011 came from. So the reason that we have this on here is that because when we see these element diagrams, we're not given the different isotopes of every atom. But what this average atomic mass is telling us is that it is the average mass of every isotope that is possible in nature. So for carbon 12, there's 2 isotopes that happen naturally in nature. We have carbon 12 and carbon 13, and carbon 12 is actually a lot more common than carbon 13. So in every 100 atoms of carbon that you might have, 99 of those will be carbon 12, and then just 1 of those will be carbon 13. And so there's just a small calculation. We won't get too into it, but that's it considers how common each of these isotopes is when calculating the average mass of every carbon atom. Now, we've talked about atoms and we've talked about isotopes, and the last thing to talk about in this video are the ions. Now, before we get into it, I just want to remind you that when we're talking about atoms, they're usually neutral in charge, and this is because they have the same number of protons and electrons, and because these two have opposite charges, they cancel each other out. They balance out their charges. So now, for this next section, we're going to be using this handy little formula to calculate the ionic charge, where we just take the number of protons in an atom and we subtract the number of electrons from it, and this will give us the overall charge on the atom. So now if we look at this model on here, we have an atom with 3 protons in the center. So these are 3 positive protons, and we have 3 negative electrons surrounding it. So if we just list that all that out, we have 3 protons and we have 3 electrons. And so if you apply this formula to it, you take 3 protons minus 3 electrons, we get an overall charge of 0. Now, there's some cases when it doesn't work out this way, where we don't have the same number of protons as we do electrons. And so when this happens, our charges don't balance out and our atom ends up having an electrical charge. Now, when this happens, we have a new name for those charged atoms, and they're called the ions. And so if we look at these two other examples, we have a negative ion on the left and a positive ion on the right. So let's look at why each of these are positive or negative. So in this example, again, if we look at that nucleus, we have 3 protons, and if we count around it, we'll see that we have 4 electrons. Now, if you apply the same formula up at the top, you'll take 3, subtract 4 from it, and overall you get a result of -1. So this means that this atom will have a negative charge of -1, so you can call it a negative ion. Finally, on this example on the right, if you count out the protons in the nucleus, you get 3 protons. In the orbits around it, you get 2 electrons. So again, if you take 3 protons, you subtract 2 electrons, you get a result of +1, meaning that this atom will have a positive charge of 1, so you can call it a positive ion. All right, so with that, wraps up everything that we need to know about the structure of an atom, and we'll be getting some practice on that in this next section. So watch this next video that follows so you know what to do for our simulation that we have on the computers.